What specific problem does the new method or algorithm aim to solve regarding knowledge editing in large language models?
The new method aims to develop a mechanistic understanding of the impact of knowledge editing, K, on large language models, LLMs, by addressing two specific problems. I. Identifying how a model expresses knowledge about a predefined set of entities in its representations, and E. Investigating how this mechanism is affected when K is applied to alter facts related to those entities. The research highlights the phenomenon of representation shattering, where the model's latent representations become heavily distorted after an edit, leading to a complete destruction of the knowledge graph structure. This distortion correlates with the distance of the edit in the graph, suggesting that the further an edit moves a node from its original position, the more detrimental the effects on the model's factual and reasoning capabilities. Overall, the method seeks to explain why K can harm a model's abilities by analyzing the changes in its internal representations in a structured knowledge graph context.
How does the proposed method or algorithm work? Illustrate it step by step, including the data generating process and how the knowledge graph is utilized in the training of the transformer model.
The proposed method utilizes a structured knowledge graph to systematically study knowledge editing, K, in transformers. First, a knowledge graph is constructed, consisting of entities and relations that define how these entities are interconnected, allowing for the representation of facts and their relationships. The data generating process involves creating sequences of alternating entities and relations, resembling paths in the graph, which are then used to train a transformer model through next token prediction. During training, the model learns to encode the global structure of the knowledge graph in its latent representations. When applying K, the method targets specific relations in the graph for editing, while retaining other relations to minimize unintended changes, and evaluates the impact of these edits on the model's performance, particularly focusing on the phenomenon of representation shattering, which occurs when the model's internal representations are distorted due to the edits.
Can you come up with a simple yet illustrative example on the inner workings of how knowledge editing alters the representation of a model? Walk through the steps with an example of a specific knowledge edit.
A simple illustrative example of how knowledge editing, K, alters a model's representation can be seen through a corrective edit involving the entities January and February in a cyclic knowledge graph of months. Initially, the model correctly associates the fact that January is followed by February. If we apply a corrective edit to change this fact to January is followed by March, the model's internal representation undergoes significant alteration. This edit introduces a distortion in the model's latent representations, leading to what we term representation shattering, where the global geometry learned during pre-training is disrupted. As a result, the model may incorrectly infer that February is now associated with March, thereby losing the coherent understanding of the cyclic order of months. The extent of this shattering correlates with the distance of the edit. In this case, the change from February to March, a distance of 1, results in less distortion compared to a hypothetical edit from January to July, a distance of 6, which would likely cause even greater degradation in the model's reasoning and factual recall capabilities.
What are the theoretical or practical benefits of using structured knowledge graphs for investigating the effects of knowledge editing compared to other approaches?
The use of structured knowledge graphs for investigating the effects of knowledge editing, K, offers several theoretical and practical benefits. Firstly, structured knowledge graphs allow for a clear representation of how entities and their relationships are interlinked, which facilitates a precise understanding of the global structure that the model learns during training. This structured approach enables researchers to visually delineate the global effects of distorting a fact, as the graph's organization can be systematically altered and analyzed. Secondly, by employing a controlled and interpretable setup, researchers can isolate the mechanisms behind K's detrimental effects, such as the phenomenon of representation shattering, which is correlated with the distance of edits in the graph. This contrasts with other approaches that may lack such clarity and control, making it difficult to derive concrete hypotheses. Lastly, the findings from synthetic settings using structured knowledge graphs are likely to generalize to broader contexts, as indicated by preliminary investigations with larger models like GPT-2, thus enhancing the applicability of the research outcomes.
How is the proposed method validated or tested, particularly in terms of measuring the impact of knowledge editing on model performance and reasoning capabilities?
The proposed method is validated through a series of evaluations that measure the impact of knowledge editing, K, on model performance and reasoning capabilities. Specifically, the model's ability to recall facts seen during training is assessed through direct recall accuracy, while logical inference accuracy evaluates the model's consistency in inferring relationships among held-out relations. Additionally, compositional inference accuracy measures the model's ability to generalize beyond the training data by assessing its performance on compositions of relations. The study also employs a quantitative analysis of representation shattering by measuring the change in the geodesic distance matrix before and after edits, correlating this with the model's performance metrics. Finally, the method is further tested using a pre-trained GPT-2 model, where counterfactual edits are applied to concepts with cyclic orders, demonstrating that as the edit distance increases, both representation shattering and accuracy decline, thus validating the hypothesis regarding the detrimental effects of K.
What limitations or drawbacks does the proposed approach have in understanding knowledge editing effects, especially in relation to generalizability beyond the toy settings used in the studies?
The proposed approach primarily utilizes synthetic knowledge graphs to investigate knowledge editing, K, effects, which may limit its generalizability to real-world scenarios. While the findings indicate that representation shattering occurs in controlled settings, the authors acknowledge that their analysis is primarily confined to these synthetic environments, raising concerns about how these results might translate to more complex naturalistic data. Additionally, the study's reliance on a simplified model, such as the two-layer nano-GPT transformer, may not fully capture the intricacies of larger pre-trained models like GPT-2, which could exhibit different behaviors under K. The authors suggest that while preliminary investigations with GPT-2 show similar trends, the extent to which representation shattering and its detrimental effects on reasoning capabilities hold true across various contexts remains uncertain. Thus, the mechanistic insights gained from the toy settings may not comprehensively address the broader implications of KE in diverse, real-world applications.